Okay, so let's keep talking about tangent lines. And here in this example, what we're going to do is actually try to find the equation of a tangent line to a given curve. So it says find an equation of the tangent line to y equals x squared at the point 1, 1. So first thing we should do is recognize or identify that point 1, 1. Okay, so here's the point 1, 1 right there. Okay, and we want to draw, we want to find the equation of the line that's tangent to it. So I'm going to try to draw a tangent line here carefully. Decent. Okay, so that blue line is tangent to the red curve at that point, right? So it touches it once and is going in the same direction. So if you are walking along the red curve and I'm walking along the blue line, when we get to 1, 1, we'll be going in the exact same direction. Only at that one point we'll be going in the exact same direction. All right, so let's think about this a little bit. In order to write the equation of a line, this line here, I'll call it L, that line L that we're looking for. If we want to find the equation of a line, we need to know two things. We need to know the A point on the line, just trying to write a better L, a point on the line, and we need to know slope. So if we know a point and a slope, then we can write the equation of the line. Well, we do know a point. There's our point 1, 1. We know that point is on the line. What we need is a slope, but in order to write the slope, we have to have 2 points. And we don't have 2 points. We only know one point that's on this blue line, right? We're trying to write the equation of the blue line, and we only know a single point, and we don't know the slope. Okay? And in order to know the slope, we have to have 2 points, which we don't know, so we're kind of in a trap here. So what we're going to do is we're going to approximate the slope of the tangent line with a secant line. If you'll remember, just real quickly, a secant line goes through a curve at 2 points. That's the difference between a tangent and a secant. A tangent touches the curve at a single point. A secant goes through it at 2 points. You'll remember that looks something like this from geometry. This would be a secant line. So let's think about secant lines for this curve here. What I'm going to do is actually sort of zoom in on this region right here. So I'm just going to look right here and zoom in on this space right here. So we would have, and I actually just say, whoop, there's my guy. So we would have that red curve, and I'm going to exaggerate the curvature a little bit to make my diagram a little more visually discernible. And we have this red curve, and we know we have the blue tangent line, and I'm going to say it goes through at 1, 1, right? So there's our tangent line L. That's what we're concerned with. And we're going to look at secant lines that also go through 1, 1. So go through 1, 1, and then go through some other point on the curve. Okay, that's a little sloppy here, a little too sloppy. That's not much better. It's hard on this tablet. So that one's okay. So here's our secant line, right? That's the secant line. The blue line is our tangent line. And what we're saying is that this green line is clearly not the blue line, but it's somewhat close to the blue line is the idea here. No, it's not super close to it, but if we consider lines like this or lines like this, the first green line that we drew is much closer to the blue line than those other ones, right? So the secant line approximates the tangent line, okay? That's what we're saying. We're going to approximate the tangent line using a secant line. So the secant line is approximately the same as the blue tangent line, which means that the slope of the secant line is approximately equal to the slope of the tangent line. Right? I'm going to call that slope m. That's the slope that we're interested in. Okay. So if I label these 2 points here, the point that we were given we'll call P. We know it's 1, 1. And this other point here, I'll call it Q. Well, I don't know where it is, but I know it has some x value. And the whole idea is I drew it so that's on this red curve, which has the function y equals x squared. So the corresponding y coordinate would be x squared. So point P is known to be 1, 1, and point Q is some other point on the curve which has coordinates x comma x squared. Okay, which means that the slope of PQ, that is to say my secant line, let's say it this way, my slope of the tangent line we know is what I'm looking for, that's m, and that's approximately equal to the slope of the secant line. The slope of the secant line is the slope from P to Q. the secant line goes from P to Q. So the slope of the tangent line is approximately equal to the slope of PQ. And we know that the slope of PQ by the slope formula would simply be given by change in y over change in x. Change in y over change in x. So our known y coordinates here, we have x squared minus 1 are the y coordinates, x squared minus 1, over x minus 1 are the x coordinates. So this would give us the slope of the secant line, which is approximately equal to the slope of the tangent line, if I just say slope of the tan line here, right? So what I need to do now is let's pick some specific values for a Q. Like let's just suppose for Q, x equals 1.5. That's a number that's not equal to 1, so we know it won't land on P, but it's close to 1. So let's pretend that Q falls at x equals 1. Well, this would mean that y equals 1.5, x equals 1.5, so y would equal 1.5 squared, which is 2.25, which would mean that the slope of PQ is 2.25 minus 1 over 1.5 minus 1, which is 1.25 over 0.5, which ends up being 2.5. Okay, so when x equals 1.5, our slope of the secant line is 2.5. And what we're saying is that because we're saying that the secant line is approximately equal to the tangent line, then we're saying that this is approximately equal to the slope of the tangent line. Approximately. It's a rough approximation, again, because this green line is not super close to the blue line, but somewhat close. And so we can say that the slope of the tangent line is somewhat close to 2.5, which is the exact slope of this particular secant line. But what would happen if we move a little bit closer? Let's pretend that Q is not so far away. Let's move Q a little bit closer and say, let's put it at x equals 1.1. Well, if x were at 1.1, then our slope would be 1.1 squared, which is 1.21, minus 1.1, right? This is 1.1 squared. That's where we're getting that. That's a little hard to read. Okay, but remember, we're just squaring the x value to get the y value. And then we have, in the denominator, we'd have 1.1 minus 1, which is 0.21 over 0.1, which 0.21 divided by 0.1 is going to be 2.1. And so that, again, is an approximation for the slope of the tangent line, approximately equal to the slope of the tangent line. Okay? But the fact is, because we moved Q a little bit closer, right? If we said Q is at 1.5 and then we said let's move it in, now Q is at 1.1, it's a lot closer to P, which would cause our secant line to be a lot closer to the blue line, right? And so this is in fact a better approximation of the slope of the tangent line. And so what we recognize here is, what I really would like to do is just keep moving this x value closer and closer and closer, because the idea is, if I draw a really exaggerated curve, if this is my tangent, the secant line, as this point here comes in closer and closer, as Q moves in closer and closer, my secant line is going to get closer and closer to the tangent line, right? As I get really, really close, the secant line is going to get really, really close to the tangent line. So we could say, as Q goes closer and closer to P, the slope of PQ gets closer and closer to the slope of the tangent line. So what we're going to do is just make a table of values here and make basically find our first limit to figure out what this slope would be. So what we want to do here is just say, let's pretend we get to choose our x values, and then we're going to find the corresponding x squared value, which will allow us to compute the slope of PQ. We already did it at 1.5 and saw 2.25, and that gave us a slope of PQ that was 2.5. That was our first approximation for the slope of the tangent. Then we did 1.1. That was our corresponding y coordinate, and we don't necessarily need that middle column actually. The point is just that the slope is going to be given by x squared minus 1 over x minus 1, right? That's the slope. So that's why we need to know x squared. We don't necessarily need to write that column in there. But the slope of PQ, again, would be 2.5 for the first x value. As we get closer, we saw that move to 2.1, and then we would just want to keep moving in closer. So we'll go to 1.1, 1.01, 1.001, and see what happens to the slope. And so I filled in these for you to save some time here, but as x gets really close to 1, we see that the slope of the secant line gets really, really close to 2, right? And what we would want to do also is say, all right, well, that's good. If as q goes toward p from this right side, we can see that the slope is getting really close to 2. So that makes us think that the slope of the tangent line is going to get close to 2 and actually is going to be 2. And we would also want to verify that from the left side as well. And we'll talk about that more later on when we get more deep into limits. But what we can see here is that as x gets really close to 1, the slope of PQ gets really close to 2. Or as x approaches 1, we would say that the slope of PQ gets closer and closer to 2. Or as x approaches 1, slope of PQ approaches 2. Which is what we're going to see here on the next page here. It says, as x gets close to 1, the slope of the secant line appears to be getting very close to 2. And the idea was that, again, as q moves toward p, this secant line becomes more and more like this tangent line, or the green line becomes more and more like the blue line. And so if the slope of the secant line is getting really, really close to 2, we're going to go ahead and say that the slope of the tangent line is, in fact, the limit of these slopes. And what we mean by limit is the value that they are going closer to. So what we can say is that the limit, we're going to talk more about the notation of limits, but the limit as that point Q gets really close to P, the limit of the slope of PQ is exactly equal to the slope of the tangent. And in fact, what we're seeing here is that the limit in algebraic form here, what we're saying is as q moves closer and closer to p, what we're saying is x moves closer and closer to 1. So we can say the limit as x approaches 1 of our slope, the formula for slope of PQ was x squared minus 1 over x minus 1, right? We saw that up here. So the limit as x goes toward 1 of x squared minus 1 over x minus 1 equals 2. And therefore now we're able to make a conclusion here that if the slope of the secant line is getting closer and closer to 2, we're going to go ahead and conclude that the slope of the tangent line is in fact 2. And then now we're able to go ahead and actually write the equation of our tangent line, okay? The whole point of this problem was to write the equation of the tangent line, and it's been a long road getting there, but this is an important form of thinking for us to develop. So now that we know that the slope of the tangent line is 2, we're able to say, all right, so if we're trying to write the slope of the tangent line, we know that it has the point P with coordinates 1, 1, and it has a slope 2. So we can use point slope form of the line to go ahead and write the equation. And really this is a fine equation of the line, so you could leave it right here in point slope form. We'll do that a fair amount when we're actually in calculus. If you wanted to simplify it into slope intercept form that you're more used to, you would distribute that 2, and you'd get 2x minus 2. When you add the 1 from the left side, you'd end up with 2x minus 1 as your slope intercept form. Either form are acceptable, but here is our equation of the tangent line. This is the equation of the line that is tangent to the graph of x squared at x equals 1, or at the point 1, 1.